Have you ever had that moment? Your machine learning experiment, it works beautifully in the notebook.
Oh, yeah. The classic scenario.
But then trying to get it into a live product,
yeah,
it just falls apart.
it's a huge frustration, a really common pain point.
That gap, that chasm between the lab and the real world, that's exactly what we're diving into today.
MLOps, machine learning operations.
Right. Our mission here is to explore MLOps, this set of practices designed specifically to bridge that gap. We want to get those models out of, development purgatory.
Exactly. Make them actually deliver value.
So this deep dive, we're going to uncover how MLOps helps deliver ML services that are reliable, scalable, maintainable, basically taking AI from concept to customer.
Doing it efficiently.
We're drawing our insights today from a couple of great sources: MLOps Essentials, Tools and Life Cycles, and the Ultimate Developer's Guide to Production-Ready MLOps.
Both really solid resources.
So by the end of this, you'll get not just what MLOps is, but really how it streamlines that whole complex journey, from idea to live AI product.
Yeah, and we'll dig into some specific tools, too.
Definitely focusing on powerful tools like MLflow and Kubeflow.
Key players in the MLOps space.
Okay, let's unpack this.
Let's do it.
So that core problem MLOps solves, the whole it works on my machine thing.
They all been there.
But with machine learning, it feels amplified, doesn't it?
It really is, because you've got this unique dependency. It's not just code.
Right. It's code and models and data, that tripartite dependency.
Exactly. Change any one of those, and suddenly things might break in subtle ways.
So revalidation, redeployment, it gets way more complex than, say, traditional software development.
Absolutely. And that's where the evolution from DevOps comes in. MLOps borrows principles, sure, but the focus shifts.
How so?
Well, in DevOps, a lot revolves around the user experience, the application's behavior. With ML, the data becomes central.
Ah, yeah.
The quality of the data, the version of the data, potential drift in the data, it all directly impacts the model's behavior.
Which adds layers of complexity.
Immense layers. And without a structured framework like MLOps, that complexity just leads to bottlenecks, inefficiency, models that never make it out the door.
Or worse, models that fail silently in production.
That's a huge risk. So what's fascinating here isn't just the tech, the lines of code, it's how MLOps forces a change in how teams interact, how they build together. It's a cultural and process shift.
That makes sense. So beyond avoiding disaster, what are the tangible benefits? You mentioned faster deployment.
Yeah, that's a big one. We're talking reducing deployment time from, say, 30, 90 days, which is not uncommon, down to, well, much less, days, sometimes even hours for updates once the pipelines are set up.
That's a massive acceleration.
It is, but maybe even more impactful is catching those silent errors we mentioned. Continuous monitoring is baked into MLOps.
So you spot data drift or performance drops quickly?
Almost immediately, ideally, instead of finding out weeks later that your model's predictions have gone haywire.
Hey, that reliability boost is huge. What else?
Improved collaboration is key. Data scientists, ML engineers, operations folks, they need to work together seamlessly. MLOps provides the framework for that.
Breaks down the silos.
Exactly. And you get enhanced reliability, better performance through monitoring and retraining, plus streamlined governance and compliance.
How does governance fit in?
Through comprehensive versioning. Versioning code, data, models, everything. It creates an audit trail, ensures reproducibility.
So it's not just about tools, it's a whole mindset shift.
Precisely. It's cultural and process-oriented first, tools second.
Okay, so if that's the why, let's get into the how. The anatomy of a production ML lifecycle. You said it's not linear?
Definitely not. It's an iterative, continuous loop. Think continuous X.
Continuous X.
Continuous integration, continuous delivery, continuous training, and continuous monitoring. It's always circling back.
Right. So where does that loop typically start?
It really should start before any code gets written, with business goal identification and ML problem framing.
Okay, so linking it to the business need from day one.
Absolutely. You translate a business goal like, I don't know, improve customer retention into a quantifiable ML problem, something like predict customer churn with at least 85% accuracy.
You need those specific KPIs, those success metrics defined up front.
Otherwise, you're just building tech for tech's sake. You need to know what good looks like.
Makes sense. What's next in the loop?
Data engineering, this is foundational. Garbage in, garbage out absolutely applies here.
So getting the data right.
Totally. Data collection, exploratory analysis, EDA, cleaning, pre-processing, feature engineering, and really rigorous validation.
Ensuring data quality. It's the fuel.
It's the fuel. Without good fuel, the best engine won't run well.
Okay, fuel tank's full now.
Now comes model development. This
Yeah.
is the iterative core, where data scientists often live.
Algorithm selection, training.
Yep. Training, hyperparameter tuning to squeeze out performance, and then offline evaluation against those metrics you defined earlier: accuracy, precision, recall, whatever fits the problem.
This is probably the part most people think of when they hear machine learning.
It is. Lots of experimentation happens here, but crucially, it needs to be structured.
Once you have a model that looks promising offline,
Then it's time for model deployment. You package that validated model and make it available in production.
how does that usually look? Like an API?
Often, yeah. A REST API for real-time predictions is very common, or it could be part of a batch processing system.
And you mentioned strategies like blue-green or canary rollouts.
Right. Ways to deploy gradually, reduce risk. You don't just flip a switch and hope for the best. You might send 10% of traffic to the new model first, monitor it, then ramp up.
Smart. So models deployed. Job done.
Not even close. That leads straight into model monitoring and maintenance. This is absolutely critical.
Monitoring for what exactly? Uptime. Errors.
That, yes, operational health, latency, error rates. But even more importantly for ML, you monitor for performance degradation.
So is the model still actually making good predictions?
Exactly. And this is where you hit things like data drift.
Okay, what's data drift?
It's when the statistical properties of the live data your model sees in production start to differ significantly from the data it was trained on.
So the world changes, basically.
Precisely. Or you might encounter concept drift.
And that is?
That's when the underlying relationship between the input features and what you're trying to predict actually changes over time.
Can you give an example?
Sure, think of a spam filter. Spammers constantly invent new techniques. If your filter isn't updated, the very concept of spam it learned drifts and it starts missing the new stuff.
Got it. So monitoring detects these drifts.
Yeah.
Then what?
Then you trigger retraining. This closes the MLOps loop.
The continuous training part.
Right. Feedback from monitoring, maybe accuracy dropped below a threshold or significant drift, was detected, triggers automatic retraining, usually on newer data.
And that retrained model goes back through the deployment and monitoring phases.
Exactly. It ensures continuous improvement and adaptation. It's a self-improving system, ideally.
And underpinning this whole cycle, you mentioned automation and version control earlier.
Absolutely essential. You need automation everywhere possible. Manual steps are slow and error-prone.
And version control for everything.
Everything. Code, yes, obviously with Git. But also the specific version of the dataset used, the model artifacts themselves, configurations, parameters.
Why is that so important?
Reproducibility and auditability. You need to be able to go back and reproduce exactly how a specific model version was trained, using what data, what code. It's like having that perfect, repeatable recipe every time.
Okay, that life cycle makes a lot of sense. Let's dive into the tools that enable this, starting with MLflow. You called it the Data Scientist's Command Center.
Yeah, I think that's a good way to put it. It's an open source platform designed specifically to manage the ML lifecycle, particularly the experimentation and model management parts.
And it's open and library agnostic. What does that mean in practice?
It means it's designed to work with pretty much any ML library, scikit-learn, TensorFlow, PyTorch, XGBoost, you name it. It doesn't lock you into one ecosystem.
That's a big plus. And user-friendly for data scientists.
Very much so. You can often integrate it into existing Python code with just a few extra lines. The barrier to entry is relatively low.
So what are its main parts? You mentioned 4 components.
Right. First up is MLflow tracking. Think of this as your digital lab notebook.
Okay.
It gives you an API and a web UI to log and visualize your experiment runs.
What kinds of things do you log?
You log parameters like learning rates, number of layers, any input configuration. You log metrics, accuracy, loss, F1 score, whatever you're tracking. And you log artifacts.
Artifacts like the trained model itself.
Exactly. The trained model file, maybe plots, feature importance charts, even data samples, everything related to that specific run.
And these are organized into experiments and runs.
Yep. An experiment is like a project or a task, say churn prediction. Each time you run your training script, that's a run within that experiment.
So you can easily compare different runs, see which parameters led to which metrics.
Precisely. It makes your experiments reproducible and comparable. Just running MLflow locally spins up a web server, usually on port 5000, giving you that dashboard.
And getting started is just mlflow.startrun.
Pretty much. And for many popular libraries, there's even an autolog function that logs a bunch of standard stuff automatically, making it even easier.
So this really solves that problem of digging through old notebooks trying to remember settings.
It totally does. It standardizes the metadata around your experiments.
That metadata aspect feels key. It's not just the code, it's the context.
It's absolutely the context. But treating every parameter, metric, and model version as a first-class versioned asset, you move beyond guesswork. Your results become truly auditable, reproducible. That's massive, especially in regulated fields.
Okay, that's tracking. What's the second component?
MLflow projects. These are like the blueprint for packaging your code.
Packaging for reproducibility.
Exactly. It's a standard format, usually a directory or a Git repo that contains an ML project file. It's a YAML file.
And what does that file define?
It specifies the project's name, the environment needed to run it, like a conda.yaml or a Docker container, and the entry points, the scripts to run, along with their parameters.
So anyone can take that project and run it reproducibly using MLflow Run.
That's the goal. It bundles the code and its dependencies together.
Got it. Component 3.
MLflow models. Think of these as the standard shipping container for your trained models.
A standard way to save and package models.
Exactly. When you log a model artifact using MLflow tracking, it saves it in a directory with a specific structure, including an ML model file.
Another YAML file.
Yep. And this file defines different flavors for the model.
Flavors, like different ways to use the model.
Sort of. A flavor indicates how the model can be loaded or used. For instance, there's a sklearn flavor, meaning you can load it directly as a scikit-learn object. There's a TensorFlow flavor, a PyTorch flavor.
Okay.
But the really powerful one is the Python function flavor, often called pyfunc.
Why is that one special?
Because it acts like a universal adapter. It defines a generic Python function interface, predict data frame, for the model. This means you can package almost any Python model, regardless of its original framework, with a pyfunc flavor.
And that helps with deployment.
Massively. Downstream deployment tools can just rely on the standard pyfunc interface without needing to know the specifics of how the model was trained. It simplifies integration across diverse environments.
So a model trained in PyTorch could potentially be served by a system expecting a generic Python function just by using pyfunc.
Exactly. It promotes interoperability. MLflow models also support logging input-output signatures.
What's the benefit of that?
It defines the expected data schema column names, types, crucial for validation when deploying or serving to make sure the incoming data matches what the model expects.
Right, avoids runtime errors. Okay, that brings us to the fourth component.
The MLflow model registry. This is like your central warehouse and quality control center for models.
So tracking is the lab notebook, models are the containers, and registry is the warehouse.
Good analogy. It's a centralized place to manage the entire life cycle of your MLflow models after they've been logged.
What does managing the life cycle mean here?
It provides model lineage. Where did this model come from? Which run produced it? It handles versioning. Every time you register a model with the same name, it gets a new auto-incrementing version number.
Okay.
And crucially, it supports stage transitions using aliases. You can assign stages like staging, production, or archived to specific model versions.
So you can promote a model from testing to live traffic.
Precisely. You might test version 3 in staging, and once it passes, you transition the production alias to point to version 3. This acts as that critical bridge between experimentation and tracking and actual deployment.
And you can manage this programmatically.
Yes, using the MLflow client API. You can automate model promotion as part of your CI/CD pipelines.
Okay, this MLflow setup seems really well thought out for organizing the development side. It feels like it empowers data scientists without forcing them to become DevOps experts.
That's a huge part of its appeal. It lowers the barrier to adopting good MLOps practices during development and experimentation.
You mentioned the mistake of not having a registry.
Wow.
Just versioning chaos, right?
Yes.
Model final v2, really final.pkl.
Exactly, that kind of chaos. Scattered files, no clear lineage, no easy way to roll back, no formal promotion process. The registry brings order and governance to that crucial handoff point.
Makes total sense. Now let's shift gears to the other powerhouse, Kubeflow. This sounds more infrastructure heavy.
It definitely is. Kubeflow is a Kubernetes native orchestration platform. It's designed to manage the end-to-end ML lifecycle on Kubernetes.
So it assumes you're running on Kubernetes.
Right, fundamentally, yes. Its components are actually implemented as Kubernetes custom resource definitions, or CRDs. It extends Kubernetes specifically for ML tasks.
Okay. You mentioned the trade-off earlier, the learning curve for Kubernetes itself.
That's the main upfront investment. You or your team need some familiarity with Kubernetes concepts, pods, services, deployments, CRDs.
What the payoff is.
Scalability, portability across environments that run Kubernetes, which is most clouds and on-prem setups now, and robust orchestration for complex workflows. It's built for production scale.
Got it. So what are Kubeflow's core components? You mentioned three main ones.
Right. The absolute heart of Kubeflow is Kubeflow pipelines, or KFP. This is your assembly line, your orchestration engine.
Orchestrating what exactly?
Implex ML workflows. It lets you define these workflows as directed acyclic graphs, DAGs.
Like steps in a process that have dependencies.
Exactly. Each node in that graph is a component, and crucially, each component is a containerized piece of code.
So like a Docker container running one step, data cleaning, training, evaluation.
Precisely. You define these components usually in Python, using decorators like at dsl.component. Then you use another decorator at dsl.pipeline to wire these components together into a pipeline.
And how does that Python definition become something Kubeflow runs?
You compile the Python pipeline definition into a YAML file. That YAML describes the pipeline structure, and you submit that YAML to the Kubeflow pipelines engine for execution on Kubernetes.
So it's defining your whole ML process as a graph of containerized steps, like Lego bricks.
That's a great way to think about it. Reusable, containerized bricks for your ML workflow.
Okay, that's KFP, the assembly line.
Yeah.
What's next?
Katib. This is Kubeflow's optimization engine. Think AutoML.
Automated machine learning. For what specifically?
Primarily hyperparameter tuning and neural architecture search. It automates the often tedious process of finding the best model configurations.
How does it work?
You define a Katib experiment, again, usually via a YAML manifest. This experiment specifies the search space, e.g. of learning rate between 0.01 and 0.1, the optimization objective, e.g. maximize validation accuracy, and the search algorithm, like random search, Bayesian optimization.
And Katib runs multiple training jobs.
Exactly. It launches multiple trials, each trial being a training job with a different set of hyperparameters suggested by the search algorithm. It finds the best combination for you.
That could save a lot of manual effort.
A ton of manual effort, and potentially discover better configurations than you'd find by hand.
Okay, KFP for pipelines, Katib for optimization. The third one?
Kserve. This is the serving layer, built for deploying models on Kubernetes effectively.
Serving models, so making them available for predictions.
Yes, but in a scalable, resilient, and even serverless fashion. Kserve introduces its own CRD, the inference service.
Another CRD. What does this one do?
It abstracts away a lot of the complexity around deploying models on Kubernetes. Things like creating deployments, services for networking, auto-scaling. Kserve manages that based on the inference service definition.
And serverless. How does that work?
It often integrates with Native, another Kubernetes project.
How?
This allows Kserve to scale the number of model-serving pods up or down based on traffic, even scaling down to 0 pods when there are no requests.
Scale to 0. That's great for cost savings.
Huge cost savings, especially for models that don't get constant traffic. Kserve also supports advanced deployment strategies out of the box.
Like the blue, green, or canary rollouts you mentioned earlier.
Exactly. You can define those declaratively in the inference service manifest, plus A/B testing, and it gives you a predictable URL endpoint for your applications to send inference requests to.
So Kubeflow seems to handle the industrialization part, taking models and running them reliably at scale.
That's a perfect summary. It handles the containerization, orchestration, scaling, and serving all that heavy lifting needed for production-grade ML on Kubernetes.
Okay, we've got MLflow for development and Kubeflow for production orchestration. But what about the data itself? You stressed its importance. We need data versioning, right?
Absolutely critical. It's the third leg of the stool. Code, models, and data. You need traceability, reproducibility, auditability for your data just as much as for your code.
Because the model's behavior depends directly on the data it was trained on.
Fundamentally, if you can't pin down the exact version of the dataset used for training, how can you truly reproduce a result or debug a problem? Data is the fuel, and without versioning it, your models kind of become these black boxes with questionable origins.
So how do we version large data sets? Git isn't great with huge files.
It definitely isn't. And that's where tools like DVC, data version control, come in. It's designed specifically for this problem.
How does DVC work with Git?
It works alongside Git. DVC doesn't store the large data files in your Git repository. Instead, when you DVC add a data file or directory, .dvc creates a small .dvc file. It's just a text file containing metadata, like a hash of the data and information about where the actual data is stored.
A pointer file, essentially.
Exactly. It's tiny. So you commit this .dvc file to Git. Git tracks the pointer, not the massive data set.
Okay, but where does the actual data go?
You configure DVC with a remote storage location. This could be a shared drive, an S3 bucket, Google Cloud Storage, Azure Blob Storage, even just another directory on your local machine.
So the workflow is .dvc, add the data, which creates the .dvc file.
Right. Then you get add and git commit the .dvc file,
Right.
and then you use dvc push to upload the actual beta files, tracked by that .dvc file, to your configured remote storage.
Got it. And if someone else clones the Git repo?
They get the code and the .dvc pointer files from Git. Then they run dvc pull.
And dvc pull fetches the actual data.
It fetches the specific version of the data corresponding to the .dvc file version they have checked out, downloading it from the remote storage into their local workspace.
So everyone gets the exact same version of the dataset tied to a specific Git commit, guaranteed reproducible data snapshots.
That's the beauty of it. It ensures that critical data context is never lost and that your training environments are truly reproducible.
All right, DVC for data. Now back to MLflow and Kubeflow. Are they competitors or partners? You hear them compared a lot.
It's a common question, but they're fundamentally different beasts, though highly complementary. They don't really compete head-to-head.
How do their philosophies differ?
MLflow is very much focused on the experimentation phase. It's about tracking runs, organizing experiments, packaging models, managing model versions. It's code-centric, environment-agnostic, relatively lightweight, and designed to be easy for data scientists to adopt.
The lab notebook and the shipping container.
Right. Kubeflow, on the other hand, is a full platform for orchestrating entire ML workflows on Kubernetes. It's infrastructure-centric, uses declarative YAML definitions, and is built for complex, containerized pipelines running at scale.
The assembly line and the serving infrastructure.
Exactly. It's intrinsically tied to Kubernetes and requires that Kubernetes understanding.
So not really competing for the same primary job.
Not at all. Which leads to the idea that they're actually better together. Using them in combination is often seen as the most powerful and professional pattern.
A hybrid architecture. How does that work?
Typically, you deploy a centralized MLflow tracking server on your Kubernetes cluster. This becomes the single source of truth for all experiment tracking and model registration across your teams.
Okay, MLflow lives on Kubernetes too.
Right. Then you use Kubeflow pipelines, KFP, to orchestrate the end-to-end workflow data processing, training, evaluation, deployment, etc.
And how did the Kubeflow pipeline steps interact with MLflow?
That's the crucial link. The containerized components within your Kubeflow pipeline, the training component, for instance, are configured to communicate with that central MLflow tracking server.
So the KFP training step logs its parameters, metrics, and the train model to MLflow.
Precisely. It uses the MLflow tracking API inside the container. The training component might finish by registering the validated model to the MLflow model registry.
I see. So Kubeflow orchestrates, but MLflow records and manages the assets.
Exactly. It's a beautiful separation of concerns.
Yeah.
Data scientists can focus on developing models and using the familial MLflow APIs for tracking and registration.
While MLOps engineers focus on building robust, scalable pipelines with KFP and managing the Kubernetes infrastructure.
You got it. Each tool plays to its strengths. MLflow is the system of record for development and governance. Kubeflow is the engine for production orchestration and serving.
That makes a lot of sense. Why choose one when combining them gives you the best of both worlds? Although I guess it adds some integration complexity.
It does add a layer of complexity for sure,
Right.
but the synergy is often worth it for mature ML operations. It provides a very robust and scalable setup.
Okay, let's make this concrete. Can you walk us through that sentiment analysis example using IMDb reviews? How would all these pieces fit together?
Sure, let's imagine building that pipeline. First phase, environment and data setup.
Right, Python environment, maybe a local Kubernetes cluster like Minikube to start.
Yep, and crucially, versioning the data. You'd get an DVC in it in your project directory.
Then DVC, add the IMDb dataset.csv.
Right, configure your DVC remote, maybe just a local directory for now, or S3. Then git add data imdb dataset.csv.dvc, that pointer file.
Commit the pointer to Git.
Commit it, and then DVC push to send the actual CSV to your remote storage. Now, anyone who clones the repo and runs DVC pull gets that exact data set. Reproducibility check number 1.
Okay, data's handled. Next, experimentation and model management with MLflow.
Here, the data scientist starts working. They'd likely use MLflow.setExperiment, IMDb sentiment analysis, to group their runs.
And MLflow.startRun for each training attempt.
Exactly. Inside the run, they log parameters, MLflow.logparam, like the type of text vectorizer used, or model hyperparameters. They log metrics, MLflow.logmetric, like accuracy, precision, recall on a validation set.
And logging the model. You mentioned bundling the preprocessor and classifier?
Yeah, that's a neat trick. With text data, your preprocessing, like TF-IDF vectorization, is tightly coupled with the model, like logistic regression. Using MLflow.slan.log model, you can log them together as a single pipeline object.
So they're always deployed and used together.
Clever. Very handy. And for hyperparameter tuning, maybe using hyperopt or optuna, you'd use nested runs.
Nested runs.
You have one parent MLflow run for the overall tuning process, and then each individual hyperparameter trial becomes a child run nested underneath it. Keeps the main MLflow UI much cleaner.
Smart. Okay, you find the best modder from your tuning runs.
Then you promote it. You'd likely use the MLflow client API to programmatically search for the run with the best validation metric within your experiment. Get its run ID and the logged model artifact URI, and then use the client to register that model version and transition its stage to, say, staging in the model registry.
Okay, model is trained, logged, and staged in MLflow. Now for automation and deployment with Kubeflow.
Right. Now we build the KFP pipeline. You take your Python scripts for pre-processing, training, evaluation, etc., and wrap them in functions decorated with @dsl.component.
Turning them into those containerized Lego bricks.
Exactly. You'd have components like pre-process data, train and register model, maybe evaluate model, and deploy model.
And the train and register model component, that's the one talking to MLflow.
Yes. Inside that components container, it would have code to connect to the central MLflow tracking server's URL. It would load data, train the model, log results to MLflow, and register the best model version.
Got it. What about the deploy model component?
This component would likely take the model name and stage, same as MDB sentiment, staging, as inputs. It would use the MLflow client to find the URI of the model artifact for that specific staged version in the registry.
Okay.
Then it would dynamically generate the kserve inference service YAML manifest, plugging in that model URI. It might specify using the ML server runtime, which knows how to load and serve MLflow models automatically.
So it builds the deployment configuration on the fly, using info from MLflow registry.
That's the idea. Finally, the component would use kubectl-apply-f with the generated manifest to actually create or update the inference service on Kubernetes, deploying your model.
Wow, that's a fully automated flow from training to deployment.
That's the goal of the KFP pipeline.
And then, closing the loop and production readiness. How do you actually use the deployed model?
Once kserve reports the inference service is ready, it gives you an inference URL. You can send prediction requests to it, often just a curl command with a JSON payload.
What would the JSON look like?
It would typically match the input signature you logged with the MLflow model. Maybe like data frame records, review. This movie was great.
And you get the sentiment prediction back.
Exactly. And MLflow even has utilities like MLflow models build Docker to help package the model into a production-ready Docker image if you need a different deployment path.
It's really cool seeing how those abstract concepts, separation of concerns, versioning, automation, actually manifest step by step in a real pipeline.
Yeah, seeing the concrete example helps connect the dots. You see how each tool plays its specific critical role in getting from raw data to a live prediction API, all managed and orchestrated.
Now, we focused on open source MLflow and Kubeflow. How does this knowledge translate if you're working primarily in the cloud? Are these skills transferable?
Absolutely, 100% transferable. The concepts are the same, and the major cloud providers offer managed services that mirror these capabilities, often built on or integrating directly with these open source tools.
Can you give some examples like on AWS?
Sure. AWS SageMaker is a great example. SageMaker Pipelines is very similar conceptually to Kubeflow pipelines for orchestration. SageMaker Experiments aligns with MLflow tracking. SageMaker model registry maps directly to MLflow model registry.
And does SageMaker integrate with MLflow?
Yes, it has first-class MLflow integration now. You can use the MLflow tracking API to log runs directly to SageMaker Experiments.
What about Azure?
Microsoft Azure Machine Learning, Azure ML, also has deep MLflow integration. Your Azure ML workspace can act as a back-end MLflow tracking server. And they have Azure ML pipelines for orchestration.
And Google Cloud.
Google Cloud's Vertex AI is heavily based on these open source foundations. Vertex AI pipelines is essentially a fully managed serverless implementation of Kubeflow pipelines.
So you can often run KFP SDK-defined pipelines there with minimal changes.
That's the promise, yeah. And Vertex AI also has managed services for experiment tracking and model registry, again, aligning with the concepts we've discussed.
So understanding MLflow and Kubeflow gives you a solid foundation, regardless of the platform.
Definitely. The core principles and workflows carry over. Our choice then becomes about the level of abstraction you want. Build more from scratch with open source for flexibility, or leverage managed services for speed and convenience.
Okay, wrapping things up then. If you had to boil MLOps success down to a few core principles, what would they be?
I'd say 3 things are paramount. First, version everything, code with Git, obviously, data with something like DVC, and models with a registry like MLflows. Traceability and reproducibility depend on it.
Makes sense. Version everything. What's second?
Automate everything. Manual steps are bottlenecks and sources of error. They just don't scale. Use pipeline orchestrators like Kubeflow or SageMaker pipelines to automate the entire lifecycle.
Automate everything. Got it. And third?
Monitor everything. A deployed model isn't static. It's a living system interacting with potentially changing data. Continuous monitoring for performance degradation, data drift, concept drift. It's non-negotiable if you want to maintain value over time.
Version, automate, monitor. Seems like a solid mantra.
And within that, remember the roles. MLflow is that system of record for development, tracking, and model governance. Kubeflow as the powerful engine for production orchestration and serving at scale on Kubernetes. They really are better together.
So as you, our listener, embark on your MLOps journey, maybe consider this. In a world where AI models need to constantly adapt and improve, what does production ready truly mean? How might understanding this assembly line and lab notebook thinking empower you to build AI that not only works, but lasts and delivers ongoing impact?